So hello everyone. So welcome to our this week Rigorous Efficient AI seminar. And today we're glad to have the Professor Kaiyuan from Rice University to give us this talk. Professor Yang received his bachelor degree from the Tsinghua University and obtained his PhD degree from the UMich. And his PhD research was recognized with the 2016 IEEE Solid State Circuit Society Pre-Doctor Achievement Award. And he is now assistant professor of the EC at the Rice University. His research interests include the digital and the mixed signal circuits for security, intelligent and low power microsystems, hardware security, and the circuit system design with emerging devices. And Dr. Yang received multiple best paper awards from the top tier conferences in various fields, including the best paper award at the IEEE Customer Integrated Circuit Conference, CICC, distinguished paper award at the IEEE International Symposium on Security Privacy, the Auckland, the very prestigious security conference. Best student paper award at the IEEE International Symposium, the Circuit System East Coast, and the Best Student Paper Award finalist at the IEEE CICC. So now let's welcome Professor Yang to give us this talk about the circuit system design using the processing-in-memory for the AI and the security.
Yeah, thanks for the introduction and for your invitation. It's a great honor to be here today and to share some of our recent work in this field. So first, I want to give you a brief introduction to my research, and this will also give you some context on what I will talk about today. So my group at Rice University, we focus mostly on building very low power and very small microsystems. So we used to work on like a very small Internet of Things sensor node type of devices that you see on the top left corner, that we built millimeter scale, fully integrated IoT devices that includes microprocessors, and everything is powered by solar cell. And then we look at a lot of the biomedical applications of these devices. For example, we further shrink this stacked device into a 0.04 millimeter cubic wireless and batteryless temperature sensor device that can be used in a lot of bio studies. And then more recently, we have been working on implantable medical devices that are suitable for doing neural stimulations to treat a lot of diseases that are not possible to deal with conventional medicine. And we have been doing these kind of in vivo studies in both small models like mice and rats, and also in large animal models like pigs. And our device, as you can see, shown on the right, like we make it into a form factor that is suitable for syringe injection. So the implantation process will be very easy and safe and relatively low risk. So these are the systems we built. And in order to make systems like this, of course, the fundamental stuff is we need to build these very low power digital analog and mixed signal circuits and integrate these devices into this small form factor. But that's not enough for today's devices, for next generation IoT and medical devices, because we also want to have security in these devices, as well as some kind of signal processing data analytic capabilities embedded into these devices. So the problem here will be dealing with the basic functionality like the sensing, control, communication is already very challenging in this small form factor with zero or very small batteries. So the question for adding security and computation to these devices is really how can we fit them into the extremely constrained hardware resources that we have. So in dealing with all these three challenges, our main approach is basically we want to blur the boundaries between device, analog, and digital circuit, also as well as like architecture level designs, so that we can leverage the advantages of custom design in different layers, and then really do a form of co-design to achieve the goal of building these functionalities within an extremely small form factor. So today I'm going to share some of our work on this line of research that we use processing in memory, which is an emerging computing paradigm to enable some of the security and computational primitives for AI and security. So my talk, I will first give a brief introduction and motivation for processing in memory. And then I will talk about two designs that we recently showed for deep learning. And then I will talk about a PIM type accelerator for automata processing or pattern matching, which has applications in both machine learning and security. And then lastly, I will talk about how to use memories for random sampling. So we will talk about both the more conventional binary true random number generator using like within a standard memory. And also I will talk about our recent work on how to use a PIM structure to generate arbitrarily distributed random numbers. And last, I will conclude the talk. So in a lot of memory-centric computing that you have a lot of data involved, such as deep learning and many security applications like intrusion detection or even cryptographic computing, you will face this so-called memory wars because with Moore's law, the energy you spend and the delay you spend on arithmetic, on logic is getting much smaller compared to the energy and delay you spend on reading from memories. So even reading from on-chip SRAM, like static RAM, it's taking more energy and delay than doing a lot of like 32-bit floating point multiplication. And needless to say that if you want to read any data from an off-chip DRAM, which sometimes is necessary because of its higher capacity, then your overall energy is largely dominated by this off-chip read access. Therefore, your overall energy will be dominated by this data movement and memory access instead of your actual arithmetic operations. And this is why the processing in memory concept has been introduced. So the basic idea is that a conventional memory, a conventional random access memory, is based on address. So you provide the address and then you read one row of data from your memory. So now if you want to do computing on multiple different operations, then you need to read data from the memory sequentially in multiple cycles. But what if we can read all the data together in maybe one clock cycle? And then in the meantime, we already do some of the computing within the memory in an analog fashion. That will theoretically give us a huge energy and throughput improvement. Because now, instead of accessing the data in memory sequentially, we can access everything in parallel. And also, it has been shown in a lot of previous study that for low precision arithmetic, doing them in analog domain is going to give you some energy gains compared to doing them in digital. So this PIM concept is really, we combine this parallel access of data with the very high efficiency of analog computing. And overall, you can see that here, I list the equations for the read energy of the array. For the conventional digital computing, you access a SRAM of m by n size sequentially, and then your total energy will be proportional to m times n times the bitline bitline energy. Well, if you do the PIM type structure, you will amortize this total energy by m times, so that your overall energy is only n times the single bitline energy. And this is really one of the key things that we want to save. And this also means that you want to have a large enough m in order to compensate some of the other energy overhead you have with a PIM structure. Like you can see here, you need the ADC for PIM because your computing is done in analog, and ultimately you still need to convert it back to digital for storage and for further processing and for some floating point processing, like for the activation functions or batch normalization. And you want to amortize those energy by having a large array. So you can access many things in parallel. You do a lot of computing. So the overall effective per bit energy will stay low. So comparing different architectures of implementing like a memory-centric computing problem. So for example, a convolution neural network, we can compare this CPU type, like von Neumann architecture, and then dedicated digital architecture, mostly based on systolic arrays. And then there's also mixed signal accelerator that tries to use the analog computing for the main arithmetic part, but the overall architecture still stays like a digital accelerator, so the data will still be read from memories. And then the most recent in-memory computing or PIM structure that do both the memory access and analog computing inside a memory array. So comparing this, so the PIM will achieve the highest energy efficiency because it is analog domain, and also you amortize some of the memory read access energies. And the computer density will also be high because you don't need separate memory and arithmetic unit. You do both the data storage, the data access, and the basic computing inside the memory. And therefore, you already have a better density. So this computing density is typically defined as throughput divided by your chip area. So PIM will be very good at energy efficiency and computing density. This makes them very appealing for resource-constrained devices. So the typical penalty you pay for PIM type structure is you lose a lot of flexibility in supporting like a diverse type of models. But given the applications that we want to do a very efficient, very low cost inference on edge devices and on like sensor node, and even on like the biomedical devices that I just showed in the first slide, we probably don't care that much of flexibility. We have a known type of model or type of structures that we want to run. And therefore, that's what you pay for this higher efficiency and density. And then the last thing that is very important is the first two type of devices, they are purely digital, which means they will work very accurately as the software asks it to do. While the mixed signal accelerators and the PIM structures, they do analog computing, and analog it's naturally associated with physical noise and also with process variations in the chip fabrication. So this will result in degraded accuracy when you do this kind of PIM acceleration. So a very important challenge to deal with in designing circuits and chips for PIM is to maintain an acceptable level of computing accuracy while still enjoying the benefit it brings in terms of efficiency and computing density. So here I show a timeline for for development of Teambased computational primitives in my group. So we started to look at Team back in 2017. That we find that for cryptographic acceleration, like for elliptic curve cryptography, for AES, for a lot of hashing algorithms, that you need to do very wide word arithmetic. And this data is typically stored in a memory. And if you use a typical like 64-bit or 32-bit microprocessor, then you need to divide it into many small segments, and then you need to repeatedly access the memory and do the arithmetic, which is kind of redundant and energy waste. So we developed a special cache for a ARM microprocessor. So as shown on the bottom left. So we replaced one of the cache bank with a custom 8-transistor SRAM array. And this 8-transistor SRAM array can actually do bitwise logic operations between two rows of data. And that is very useful for accelerating a wide range of cryptographic algorithms from like private key to public key and also to hashing algorithms. So with this one, we call it a coprocessor because it's still programmable. It only replaced one of the cache bank by this computing memory. And then we get roughly like 10 times of energy and throughput improvement over a baseline like ARM processor of the same design, the same technology, without losing much of the programmability. So that's the first work. And then the second work that's relevant is in security applications, having random numbers is extremely important for like generating secret keys, for doing a lot of like, authentication process. So we find that within a commercial magnetic RAM, so which is a type of emerging memory that is planned to be used in a lot of non-volatile storage and as well as like processing in memory computing applications. We find that within this memory, we can actually convert it into a random number generator with pretty high speed and very low design overhead. So the memory can still be used as a typical memory in most of the time. And if you want to use it to generate some random numbers, you can easily convert it online. And the overall area overhead and energy consumption for doing this is very low. And then the next thing we looked at is the automata processing or pattern matching. So we specifically start from the network intrusion detection application, but later, like we are also extending it to a more programmable type of architecture that can support some machine learning, some bioinformatics, and some security applications. So for this one, we start to look into like custom designs that will further improve the efficiency and computing density for this pattern matching algorithm. And then in the meantime, we start to look at deep learning applications and see how we can use these custom circuit designs to develop like very efficient primitives for doing the multiply and accumulation operations that's critical for deep neural networks. So we demonstrated the first charge domain multibit P micro that is also using the industry standard 60 SRAM. So for those not familiar with like circuit design, 6-transistor SRAM is what we use in industry in almost all the SRAM designs today. And they are very well optimized. They are very well supported by the foundries, and there are plenty of IPs to make them work properly, and they scale very well with Moore's law, with technology scaling. and the area is typically very small because foundries will make special optimizations for this SRAM. And therefore, if you use standard 60 SRAM, you will get the most reliable memory and also a very small footprint compared to any kind of custom memory. So that's why it's important that we find a way to use 60 SRAM while still being able to do multi-bit and accurate charge domain PIM computing. And after that, we only made one compromise in this first design, which we call CapRAM, is that we introduced a semi-parallel structure that you don't really use all the rows in an SRAM bank, and that will lead to reduced throughput and energy efficiency. So we developed a different solution that is based on a custom 8-transistor SRAM, and we call it MC² RAM. So this one basically have all the checkboxes that we want. So it is fully parallel. It doesn't require any drivers that I will explain later, and it's accurate in charge domain computing. And the energy efficiency and computing density is great, and it supports programmable multi-bit precisions for the computing. And then the last thing I will also introduce today is that we built the first in-memory random sampler for an arbitrarily distributed random variable. So this one has a lot of applications in security as well as machine learning, especially statistical methods for machine learning. So I will introduce that as well today. Yeah, so I will start from the in-SRAM computing circuits for deep learning and matrix multiplication. So the problem here, it's very clear, at least at the core circuit level. We want to accelerate parallel, multiply, and accumulate operations, which is the core for convolution neural network layers, and also for it can also be used for fully connected neural network layers. And for each filter, basically you want to do this, you multiply weight with input at different index, and then you sum them up. And ProcessingInMemory will be a suitable technology for doing this because you are repeatedly accessing the weight, right? And also the same input will be used for a different weight. And that means if you store the weight in a memory and then you provide the input, the same input can be shared by many columns of memories, and they can do the computing on different weights but same inputs in the same time. And that will greatly improve the overall throughput and improve the energy efficiency. So, so that's why a lot of people are looking at PIM type or neuromorphic type designs for accelerating neural networks. So for us, we are mostly focused on SRAM-based PIM structures because we think there are a few key advantages of SRAM-based design that are difficult to be matched by other emerging devices or emerging memories in the near future. First, for a lot of for example, resistive RAM or other emerging memory devices, the programming, they can support multi-bit storage and programming theoretically, but when you actually do that, there will be a spread, and you cannot very accurately control what data is being stored. And there's also critical problems that the retention of this data in the memory is not perfect, so that the weight, the value stored in the memory will gradually lose or change over time. And that will cause a lot of challenges to the design. It can be dealt with to some degree by algorithm changes, architecture changes, or training different type of models. But they are those are extra overhead in terms of both training and testing, and you still cannot get a perfect solution. And second is that SRAM is scaling very well with Moore's law, with the scaling of CMOS transistors. So for example, in 2020, TSMC demonstrated a PIM structure in 7 nanometer CMOS, and like SRAM is already working in more cutting edge generations, like 5 and 3 nanometers. And it's not hard to believe that PIM can also work in those like very cutting edge technologies. Well, these non-volatile memories, emerging non-volatile memories, they are still stuck at relatively old generations of technology node, and it will take a considerable amount of time for them to really catch up with like what SRAM can do today, if that's possible. And the third problem with conventional, emerging like non-volatile memories is that their memory cell can be very small, which is why a lot of people think it will be great for doing PIM. But in reality, a lot of these non-volatile memories, they require high voltage to program. They require complex control and timing to read, so that their peripherals, which are the circuits that you need surrounding your memory array to really do the read, do the write, and do the computing, to control the computing, it's much larger than what you need in SRAM. Because like SRAM, it has relatively large dynamic range in terms of programming and reading and writing. So the circuit you need is really minimal. Well, for a lot of this emerging non-volatile memory, you need complex stuff to do these things. So as you can see, comparing these two designs, on top is an RAM array. The array itself is really small, but you spend a lot of things on these peripherals. Well, for a state-of-art like SRAM-based PIM array, you still get something similar to a typical memory array that most of your area is occupied by the memory cells instead of by the peripherals. So based on these three key advantages, that's why we are focusing on the SRAM. And in addition to this, like SRAM is also much easier for prototyping and for silicon demonstrations, which is really critical for PIM type of research because of the analog nature of these operations and the importance of maintaining a good accuracy in analog computing. So here I will show some abstracted models of different prior arts. So the first initial ideas for an SRAM-based PIM is mostly based on current domain computing. And the idea is that you have a column of memory cells and they store different weight. And then you give input horizontally to all the columns. And then for each cell, you will have a switch. This switch will be controlled by the input. If your input is 1, this cell will be connected to the vertical bit line. If it is 0, then you disconnect them. And then when the cell is 1, you will have a current flowing into the cell. Well, if the cell is 0, you will have no current. And overall, what you get is on this bit line, you have a total current. That is the summation of all the current going into each cell. And you can see only when your weight is 1 and your weight is 1, your input is 1, you get the current. In all the other cases, you don't get a current. So that ideally, what you get on the bit line will be the number of ions you get, and that is exactly the MAC operation we want. And this design, it has very small area, and there are several demonstrations that shows that they can use like the standard in the industry 6 transistor SRAM cell for doing this current domain computing. But the main problem associated with this type of design is first, it suffers from the non-idealities of transistors. So transistors are not perfect switches. So they are like a 3-terminal, 4-terminal device that has a lot of non-linearity inside. So for example, this input switch, when you turn it on and when it's providing the current, this current is not a constant current. It will change depending on the voltage on your bit line. And it will also change depending on temperature. It will also change depending on process variation. So that the actual result you get on this bit line will not be as accurate as you want. So here we are showing a simulated results for current domain computing. We are already doing a design trick that you only use half of the voltage range, which gives you much better linearity. If you use the full VDD range, then your linearity will be extremely bad. So we are already using only half, but you can see this linearity of the right line is not perfect. And there's also variations around each point due to process variation. And this blue curve is showing the slope at each of the points, which help you better see that it's not linear, right? If it's linear, this slope should be a constant value. And the other problem for current domain computing is that you typically suffer from a very low parallelism. So this is not very apparent, but the actual reason is that if you want to do a high parallelism, which means you want to have a lot of cells connected to the same bit line for doing a max computing, you need to really have a very low I-on and I-off current. Otherwise, your bit line will be discharged very fast and then quickly to ground, and you don't have any room for further computing. So you have to make this current very small. But as you make this current very small, you will suffer more from all those non-ideal effects from transistors. So that's exactly what we show here. So depending on your word line voltage, this is controlling how much current you have for I-on and I-off. If you have very small voltage, which means small I-on, you can potentially have more active rows, like up to the number of 100, which is pretty like a sweet spot value. You also don't want these active rows to be too large, because that will limit the flexibility for deploying models. And also the gains from the energy amortization will diminish. So, so this 100 is quite nice, but then you will have the problem of suffering from very large variations. So here we are showing the mean over sigma value. This means like the smaller this value is, that means you suffer more from process variations. So you can see at like this point, you suffer like almost 7 to 8 times more variations compared to your work at a high voltage. Right. So these are what we believe the fundamental challenges for doing current domain computing. And this is still with SRAM, which at least have an accurate storage of the 1 and 0 here. If this is replaced by like emerging memories, then it will have even more challenges in ensuring its accuracy. So the improvement over the current domain computing is based on charge domain computing. And there are 2 specific implementation methods. So the first one is called capacitive coupling. The idea is that I store the input on the top plate of this capacitor, and then I drive it to either 0 or 1 based on the memory cell I have here. And then there will be capacitive coupling between like this capacitor and all the capacitors on the same column. And the final voltage on this bit line will be dependent on how many capacitors are connected to VDD and how many capacitors are connected to ground. And you can write down the capacitive coupling equations to show that this is indeed a multiply and accumulate operation. And for this one, because it's using capacitors to do the final computing, it is much more accurate than using the current, because capacitor is a passive device. So it is much more ideal when you implement them inside like a silicon chip. So it's kind of solve the accuracy problems, but the structure proposed in this paper, they cannot support multi-bit MAC, so they are limited to 1 bit and XOR net, which are very useful for like a lot of maybe edge applications, but it's not like flexible enough to deploy different models and to support different applications. And then the other class of charge domain computing is based on charge sharing. And the idea of charge sharing is that you store the input data on the capacitors, and then you short all their top plate. And then based on this charge redistribution, you will get a final output. So similar to the coupling, you get a similar accuracy. And also this one can support multi-bit. But the limitations in the previous works is that they have relatively large area. They require custom memory cells that are like 2 to 3 times larger than a standard 60 SRAM cell. And that means you have like half or a third of the storage and computing density. By looking at these prior works, we summarize some of the design challenges for in SRAM PIM macros. So the first one is the accuracy of the analog computing. This includes the linearity, the robustness to PVT variations, the linearity and noise of the analog to digital converters. And the important thing here is that this accuracy has a trade-off with the array size. We typically want to have a very large array size because we want a higher throughput and we want more energy amortization, so you get better efficiency. But then as you increase the array size, you will suffer more from these accuracy problems. And also, when you have more computing operands where you have the same ADC resolution, you will naturally lose some accuracy, lose some information during this analog to digital conversion. And therefore, you really want your raw computing results to be very accurate. And we have done some studies on this using like trained and quantized neural network models. And we see that there's indeed a significant impact like to the accuracy of the model, depending on the array size. If your array size is really small, then you suffer much less from this, which is the results like presented by some of the papers, but they don't really enjoy a lot of the energy amortization advantages of PIM architectures. And the second desired feature is we want to do multi-bit, which means we want to support like programmable or flexible precisions for both input and weight. And also the conventional way to do that is you do 1-bit computing every time, and then you do a lot of partial sums, and then you combine them together by doing shift and add. But in that method, your throughput is really reduced a lot by the number of bits you need to support. So that ideally we want to be able to naturally do a multi-bit multiply and accumulate within the memory array instead of doing them in the digital. And third is the ADC remains to be the energy bottleneck in the in-memory computing. So the computing itself is amortized a lot, and it's basically the SRAM access energy, so it's not a big problem. And ADC energy is much more challenging to reduce because there are many different ADC challenges when you use them in a PIM macro. You have to make the ADC really small so to match the memory pitches or the width of memory cells. So that limits a lot of the like design techniques that are very, very well known and very commonly used in the ADC, in the conventional ADC design community. And you have to have new structures and new methods to improve the ADC accuracy, reduce the energy while still maintaining a very small area. And the other challenge that we find in a lot of these works is that they require extra analog drivers which are circuits that drive an analog voltage, and they are typically made out of OPMs, operational amplifiers that are very energy consuming. So we did some rough calculations for both the input, the DAC driver, and also the output, the ADC driver. And we can see that these are some data from some papers, like for the input, for driving the input, the driver is taking like 80% of the total energy, while the actual charging of this word line is only 20%. And therefore this 80% is burned by this driver itself. It's not really to the computing. And similarly for the ADCs, your input is a very delicate voltage stored on a bit line, so that you don't want to disrupt it. And you need a analog driver or analog buffer here to connect this value to your ADC. And here you will have a similar problem that this driver itself is consuming like 50% of the total readout energy. And that's really not desirable. But they are necessary if you are using conventional designs for RDC because they require an input sample. So that comes to our proposed solution. So first, for the multi-bit in SRAM computing with 60 SRAM, we have the structure shown here. So we have a cluster of 60 SRAMs. So in our prototype, we have 8 cells. So every time one of the 8 cells will be used, and then it will be connected to this cluster circuits composed of, like here we have 5 transistors. We also have a version that use 4 transistors. And this does some tricks that's shown here that help you to do multi-bit MAC operation. That means your input will be a multi-bit voltage that I sample on this capacitor. And then by playing with these switches, I can ultimately change this voltage based on the multiplication of the input with the weight. And there's a lot of details here related to how we deal with the charge injection, how we deal with the coupling of these switches. So those details are shown in our JSSC paper. So if you're interested, you can go to see that. And then for the ADC part, we are proposing a new type of star ADC that's based on charge injection. So conventionally, star ADC is based on capacitor banks, and they take a lot of area and they take a lot of energy, and also you need to sample your input on the capacitor bank, which are all the sources of the drivers that we don't want. So instead of doing that, we have this charge injection cell that can actually reuse my bitline computing cap as the input sampling cap. I don't really need to do the sampling again. So this charge injection cell only remove a certain amount of charge from my computing capacitor based on the feedback of the SAR logic. So the most of the operation is similar to a normal SAR analog to digital conversion, except that we replace the capacitive bank by this very small, purely mouse-based charge injection cells. So it makes the ADC much smaller and remove the need for the input buffers as well as the reference voltage buffers, which are typically not included if you look at the ADC paper. These buffers, they need them, but they don't report it as part of the core circuit for fire comparisons. But that's actually a significant amount of the total energy. So that when you build like a PIM system, you have to include those numbers in your overall power budget. So the overall architecture for this cap RAM is shown here. So we have these cluster structures. So here we can use the industry standard 60 SRAM cell. So although it seems like we are only using 1 out of the 8 or 1 out of the 4 cells, the actual overall storage density and computing density is quite high, even compared to some other custom memory arrays that are fully parallel, because this 60 SRAM cell is just so small compared to the custom cells made by other designs. And then we have one ADC per cluster to do the quantization, and then we have some digital peripherals that will handle the multi-bit weight. So our input is naturally multi-bit, 4-bit, but the weight limited by the SRAM technology, it can only store 1 bit. So if you want to do multi-bit weight, you still need to do the bit serial accumulation in the digital circuits. And this is the diphoto of the chip we built. So here, I emphasize a lot on the accuracy. So we did a lot of study on the accuracy, linearity of the computing. So the first part, this is actually the measured accuracy of the charge domain computing itself. It's not including the ADC. So you can see this one has an R-square value of 0.9999. It's almost perfect linearity. And looking at the derivative, the slope at each point is very constant. Right? That means we have an almost perfect computing part. And then the rest of the error is all coming from the ADC. So the one shown on the right, this is the NL, which is a measure of nonlinearity for ADCs. So you can see the overall total error is below like 1 LSB, where we have a certain sigma value for different ADCs due to process variation. So this is one of the best ADC performance that has been shown for a PIM array. So it's still not great, like compared to a single ADC design, state-of-the-art single ADC. But given all those constraints, this is pretty decent, that a result you can achieve. And then we compare different chips in terms of their computing errors. You can see their mean value is quite consistent, but the sigma indeed has some variations from chip to chip. And then here I'm showing the noise performance of the ADC and the overall computing. So you can see that for a single ADC, the root mean square noise is about 0.35 of LSB. And then for different ADCs in the same chip, their noise level is pretty consistent across the ADCs and also across the output results you get. Right, it's important because now you can just model this noise as a Gaussian additive noise instead of something that's correlated to your computing results. So comparing this CAP-RAM design with prior arts, so this is the first 60-based charge domain computing that has very good accuracy while still having a pretty good area. So you can see the area per cell. This is for the 60 SRAM itself, and then the effective area is including all the area overhead. It's better than most others in the charge domain. And if you look at the bitwise throughput, because we are supporting multi-bit input, while most of others they support 1-bit input. So the bitwise, it's so there our throughput needs to be multiplied by 4. So the bitwise throughput, the bitwise computing density, and bitwise efficiency are all pretty good in this proposed design. And we have also done some neural network test on its accuracy. So the key point is really we show it's possible to do 60 SRAM and still supporting this multi-bit weight, multi-bit input, and very accurate computing. So here I summarize this recent in SRAM PIM designs. So CAP-RAM is here. It addresses a lot of the main problems, but it still doesn't have the very high parallelism because we need to have a few SRAM cells sharing the same cluster circuit. So then in this next design, we call MC square RAM, we are adding that part as well. So this circuit is based on a new capacitive computing method. So it's still based on charge sharing, but the difference is it is now top plate sampling and bottom plate computing, which is a different scheme compared to the previous like capacitive coupling and the previous charge sharing method. Again, the details I'll not show here. It will be in the paper, in the ESOPAD paper. This one gave us the advantage that we can use very simple circuit, in reality just 8 transistors, to do a multi-bit input analog computing. So what we want to do is really, we think multi-bit input, we have done some comparisons showing that multi-bit input is really giving you a large boost in terms of efficiency and computing density and throughput. So, so we really want to support multi-bit input with as simple as possible like circuits. So what we end up having is shown here. It's 8 transistor design. It's called occupying like 1.4 micrometer square. This is around like 40% larger than 60 SRAM that we can make in the same technology using the same design rules. And this is much better than what has been shown in other works that they require like 100% to 200% area overhead. And this waveform showing how it works. So I will skip the details here. It's very important to have this switching unit that makes sure the input impedance when we do this charging, it's constant, no matter what weight you store in the memory cell. Because what we want to do is our DAC, it's a very simple current steering DAC, which is very small and very energy efficient. But that DAC requires your input impedance to be constant. So that's why we have this switching units that make sure your charging and discharging input impedance is constant, no matter what weight you have. So yeah, these are the basic offering waveform. And this is the overall structure we get. So this is the layout and the distribution of the energy. So it's again simulated in TSMC. This one is simulated. We don't have the tape measurements result yet. So it's in TSMC 65 nanometer. And you can see this one actually have fully parallel operation. So the peripheral is occupying more area compared to the previous one. But we are able to make fully parallel. Like every single cell in this array is being involved in the actual computing. This is actually rare in PIM micro designs because you need to feed the ADCs into this very small area. And this is the operation waveform. Again, for the computing part, you get a almost perfect linearity. This is in simulation, but we are confident that this one will be similar if you have a silicon measurement results because we include all the parasitics in the post-layout simulation. And then the variations of the output results are also simulated, which shows acceptable and good results. And we did some inference accuracy test, like for different ADC resolutions on this one using ResNet 20, and the accuracy is shown here. There is some degradation from the baseline, but it's already quite getting really close. And if we don't have this good accuracy, like we intentionally inject some nonlinearity here, then this accuracy will be much worse. And oh, this is blur. So comparing to the other like chart domain designs, so this one and the CapRAM one are the only ones that can support 4-bit input while having a very small cell area and computing variations. So this orange bar is showing the variations of the computing results. Basically, most of the chart domain, they can control the variation pretty well. And then the comparison will come down to the area comparison. So CapRAM, because of the semi-parallel structure, the effective area is large. And these two is the designs that have the 2 times and 3 times cell area. And this one only have like 40% area overhead compared to a 60 SRAM cell. And overall on this plot, I apologize, this is blurred somehow. But the computing density and both energy efficiency and computing density that are 2 major metrics we care about are shown here. And this proposed design is significantly improving in both dimensions while maintaining a very, very good accuracy. compared to other PIM-based devices. Yeah, so that's about the deep learning part. And next, I will talk about the other computation primitives that we are interested in to do with PIM. So it's called automata processing. It's basically a kind of a finite state automata that can be used to do like string processing, to do stream data processing. It can find many different applications in security, machine learning, in bioinformatics, in stream processing, like real-time monitoring kind of applications. And here I'm showing a very widely used benchmark for automata processing field. So you can see these are the domains they can be used for, like for security network intrusion detection, virus detection, some speech tagging, machine learning, some similarity search for DNA sequencing and other bioinformatics stuff, and some file search, malware, pattern search kind of applications. And this one, similar to deep learning, is very memory intensive because you need to store either all the raw patterns in your memory and then compare to every one of them, or you store all the information related to your automata, which basically you have a lot of states, a lot of transitions, and you need to store all this information in your memory and then find the right one to use as you see a new input. And typically your input is coming in real time, so that you need to have a very high throughput without like variable latencies. And that's why using some special memory instead of standard SRAM will be very beneficial. Classically, for pattern matching, circuit people have created something called content addressable memory, which is very widely used in like networking applications for IP lookup for these basic pattern matchings. So the idea is you store all the raw patterns in the memory, and now instead of using an address for random access, you directly give the input for the pattern you want to find, and therefore and then the memory will automatically find the rows that's storing the same data as you give, and then will tell you which row has been matched. So this is useful for like IP routing, right? You give an IP address, and then I can just look for this IP address and then tell you like which one is activated and where you should go for routing. And this one can also be used for more complex pattern matchings, but then it has a lot of limitations. And the other method is to use like this kind of state machine method, automata-based method. So here I show a very simple example that you want to search he, hers, she. So starting from the first state, the original state, if you see H, you go to S4. If you see S, you go to S1. And then ultimately you can go to like this S5 states for he, S3 for she, and S7 for hers. And if at the middle point you fail to go to E, then you will either go back to a previous state or you go back to the original, depending on the actual dictionary you have. So this one, it can be computed on software, but you need to encode all these states and all these transitions, and you need to keep looking for these things, which is taking a lot of time. So the conventional solutions are shown here. I show their energy consumption and their memory requirement. So AC is the algorithm I just showed. Like you can use SRAM to implement AC. You can use CAM to implement AC. You can do brute force TCAM. You can do like some optimized AC SRAM and some encoding method on TCAM. And they have some trade-off, right? Some is good for memory, some is good for energy, but they don't achieve both. So what we are proposing is to use PIM and combine with some both circuit and architecture optimizations. You can see that our proposed design is achieving both orders of magnitude improvement in energy and memory usage. And that's really impressive results that shows the capability of a PIM type structure. So this is the overall, we are using, at the first step, we are using the network intrusion detection as a target application. So the first chip we built is not that programmable, so it cannot support all the applications. It's just for intrusion detection, for multi-pattern matching at an unknown location in the input stream. So it's composed of 3 phases that we are using a hierarchical design, that the first one is always activated, and only when the first phase match, you will activate the phase 2, and then you will activate phase 3. So phase 1 and phase 2 will be on a custom chip, while phase 3, because of very rare activation rate, so they will be run on host processor for flexibility and simplicity. The key idea is mostly in the phase 1, that we use a CAM plus SRAM type of circuit to do the state lookup. In a conventional way of doing this, you need to store both the forward transitions and backward transitions. Forward means you are getting a good matching, and backward means you need to go back to a previous state to try to find another match. So you have much more backward transitions than forward transitions, and that greatly increase the memory usage. So our solution is that if you pipeline, we find that if you pipeline the structure and you have a PE for every depth in your state machine, then you will automatically avoid the back transition problem, because every time you fail at a deeper depth, a deeper stage, you already have a shallower stage that's doing the same computing, the same matching, and therefore you can directly go back to that without calling for explicit backward transition. So this helps us eliminate the backward transitions. And further, we are doing some circuit optimization, because for this matching based on the previous state, like for S3, it only connects to a few possible states. And this information can actually be used to selectively activate the memory ranges that you want to compare to. And that will greatly reduce the activation ratio of your memory and improve your energy efficiency. So the next optimization we do, which is a very interesting one, is that we show that you can actually use a 8-transistor like memory cell looking like this, or just half of this if you only want single port, to replace a conventional 16-transistor TCAM cell. TCAM means you can match both 0, 1, and don't care, but it requires 16 transistors, which is considerable amount of footprint. So we're reducing it to 80 by doing a special coding method. So this is the coding we do. So instead of doing the conventional 8-bit like ASCII coding, we do a fixed number of 1 coding, so that out of 11 bits, we fix the number of 1s to 5, and then you have a combinatorial possible. You can have like a few hundred possible combinations and use them to represent the ASCII code. So when doing this, you have the initial overhead of 3 extra bits, but it makes it possible to use a 8-transistor or 10-transistor memory cell for the TCAM operation, and overall your area will be improved. So this is exactly how it works. So we have, when we do the search, it's actually using a similar computing method that we used for the very first cryptographic acceleration in memory. You activate multiple rows, and then you look at the bitline voltage. And there are 4 different possible states, like 3 will give you a match, 1 will give you a mismatch. Because of the special encoding method, we can guarantee that if you have a mismatch at any point, you will definitely have another mismatch at another point. And either like one of these will make sure you have a leakage test on this bitline, so you can detect the mismatch. But the reason you need 16 transistor in the conventional design is because sometimes you have a 1 mismatch at 1 bit, it will not be shown on the bitline voltage. So that you have to have a differential version that help you to guarantee you will always see a mismatch flag. And that is addressed by the coding method instead of doing it in the circuits. So here it's showing example for matching and also for wildcard matching. Like if you store all zeros in the memory, then it will match to everything. And if you only store 0 here, then it will be don't care for this part. And if you store like A or B that they only have difference in these 2 bits, and I store just 0, 0 for these 2 bits, then I will be able to match both A and B. So that's why how it can work like a TCAM by using this encoding method. So this chip is again built in 65 nanometer, and comparing the memory usage and energy usage, it's better. It's simultaneously better in both dimensions compared to the conventional ways. And it's also having a very nice feature that the number of rules, like the scaling of energy versus number of rules is quite slow because of the special architecture. And that means this solution is very scalable in terms of the number of patterns you want to match. And it's a scalable solution for different applications. So the search energy, we have a special trick called knot gating. If you don't have it, the search energy will be proportional to your ratio of like heat patterns. But after activating this energy increase will be greatly reduced. And also the first stage is composed of different PEs, and we can do a reconfiguration of the PE depending on different heat rate. So here the search energy versus different number of stages in phase 1 is configurable, and then for different heat rates, you want to configure it to different number of depths. And that's supported by the architecture. So comparing the state of art, comparing to all the digital-based or conventional CAM or SRAM-based pattern matching engines, we have much higher energy efficiency and memory efficiency that's already shown in the previous plot. And what's interesting is if you compare to the very state of art, like for example, this one, a 14 nanometer TCAM, right? It's like 20 years ahead of us in terms of technology. Our efficiency is still like 5 times better in terms of the CAM energy itself. And in terms of the overall pattern matching, like we cannot estimate theirs. So this is really showing with this like P type of architecture for specialized functionalities, like your design can really give you a huge boost in terms of efficiency and computing density, even if you don't have the latest generation of technology. I think, yeah, I will quickly finish the last part. So the last part will be about random number generation. Random numbers are very widely used in various computational systems. And typically we want like uniform distributions. That's mostly for security and maybe Monte Carlo simulations. And we also need like binomial distributions, Gaussian distributions, and sometimes we also need an arbitrary distribution, like generate something based on a given probabilistic distribution functions. And so binary random numbers, it's easy to understand, like your secret keys, your random nonces in like security, they all are pure binary random numbers. And for non-binary sampling, it also has a lot of applications, especially in these emerging fields. First, in security, all the lattice-based cryptography, that they require random numbers. So they are the foundation for like post-quantum cryptography that are supposed to be strong even against quantum computer attackers. And also, it's very widely used for homomorphic encryption, that you do encrypting on the data without losing the information, so you can directly do computing on the encrypted data on the cloud, which is believed to be a very good, very promising solution for the security and privacy issues related to data used for like analytics and for machine learning. And then in terms of machine learning applications, there are a lot of statistical approaches, like mostly related to Bayesian methods that will require random sampling from Gaussian distributions or arbitrary distributions. So for example, there's something called a Bayesian neural network that when you calculate the MAC for every layer, you will need to do this extra noise sampling and addition. And this is also used for training process, that you intentionally inject noise in your training. And then for Bayesian method, classical Bayesian method, you will need deep sampling. This will actually require arbitrary distribution sampling and multivariate sampling from a given distribution. So these are all the possible applications that will require a random number. The first thing I will show is it's a binary random number. So this one, we are repurposing a magnetic tunnel junction based memory for random number generation. So this a magnetic tunnel junction is an emerging device that's composed of 2 layers. It has 2 different states, anti-parallel and parallel. And the conventional way, like the first paper talk about how to use this for random number generation, is to place it in a middle like unstable point. And then it will depend on noise to either go to the P or AP state. But the challenge here is you need to really find where is the 50% switching point, where is this middle point. And finding this is not easy. And you need to keep doing reading and writing and monitor the statistics in order to find a point that will place you exactly on 50%. And this line will be also temperature and process variation dependent. So you cannot just do it calibration once and use it for all devices. You have to do it again and again. So which is not easy and useful for real integration. So that the principle we find that can be used for random number generation is that instead of finding this 50% point, if you write the memory with a very low current, you will get a slow writing and with a wide spread in terms of the writing time. So for sometimes your writing will be successful very early, and sometimes your writing will be late for a given device. And this process is mostly dominated by noise, physical noise inside the device and also inside your circuit. So we want to use this as the entropy source. And the implementation is actually straightforward, but we were the first to integrate this in actual commercial MRAM technology. And we just add a 180 micrometer square block for a column to a standard MRAM array. And the normal MRAM operation is still working fine. And just when you need it, you write the memory with a very low current, and then you monitor the time. And this is what you get. So depending on the speed of your counter and the amplitude of your writing current, you will kind of get a log normal distribution. And then if you get a very wide distribution, you can harvest more random bits from this. If you get a narrower distribution, you get less bits. That will be a trade-off. But anyway, like in different temperatures, you can always get this, and you can get like 5, 6 very high quality random numbers from this process. And MRAM is known for good endurance, so it can be repeatedly written and written and read for like many times, for more times compared to other like RRAM. So it's really suitable for using them, repurposing them as random number generations. And then in terms of the non-binary sampling, what we have here is that typically what you do is you first start from a binary random number, and then you use the algorithm to generate an arbitrary distribution. And there are many common algorithms, but based on these 2 papers, they profile how much you need to spend on the random sampling. For these security applications, you can see on CPUs, they take a majority of time just doing the sampling from random variables instead of doing actual logic. And then there are some hardware acceleration methods. There are some algorithms that are more suitable for hardware implementation, like the KY sampling. There's optimized version of KY sampling and one-way sampling, and CDT sampling. It's called cumulative distribution table, that you store the CDF of your distribution in a memory, and then you find the input that's matching the pattern here, and then you can generate a number based on which point in the CDF you are matching. So the only limitation for CDT is that it's very simple to implement. It's hardware friendly, but the only thing is it has relatively low throughput. because every time you generate a new binary number, you need to compare it with all the entries in your SRAM, in your CDT table, and that is taking time. And also it's a input dependent delay. Like sometimes you just find a match very early, and sometimes it takes much more cycles. So that will be a non-constant throughput, and that will also be a security concern in terms of time domain side channel leakage. So what we propose is something called Mapler. It's an in-memory CDT sampler that addresses this problem. It provides a constant high throughput that only requires one clock cycle to generate a random number while maintaining the other nice features of CDT. So the basic principle is that you get a CDF, you give a binary distribution of U, and then you sample from this, and you get a corresponding sample result. So ideally, what you want is you have a CDF like this, you're starting from 0 to 1, and then you have a random number generator giving you a binary result, and then you compare to all the entries, like see whether it's between two entries. And then, for example, in this case, all these are smaller, these are greater, then your final sample should be coming from here. And you want it to be fast, to be low power, to be low area, and we want this to be done in a constant time. And you probably will already realize that this can be done in a kind of time circuit, content addressable memory, because we give a random number input and we find a good match. But the requirement here is not an exact match, it's a range matching. So I need to know whether it's larger or equal or smaller than the pattern inside the memory. And to address that, we developed this special memory cell that's consisting of 6 transistor standard cell plus 1, 2, 3, 4, 5, 6 plus 6 extra cells. So in total 12 transistors to do a range matching cap. So when it's exact match, you just have the match line staying at 0. And when in a smaller case, your match results will still be 0, but on this side, you will not get the results. And then in the greater case, you will get a 1 here. So in reality, you will see when your data is greater than or it's smaller or equal to. So based on this, we can just straightforwardly implement it as a random sampler. We store the CDF table in this memory bank, and then your input from a binary random number generator will be used to match the pattern inside your CAM. The only concern here is that you are doing a lot of redundant comparisons, because most of the comparisons will just finish in the MSB. You don't really need to compare to the entire row. And this entire row is typically very large, especially for security applications. It's like 64-bit or 128-bit. And that's an extra waste of energy. So our solution to that is to divide this into smaller segments and pipeline them, pipeline between them, so that you start with the MSB. If the MSB already telling you the comparison results, you don't really need to do the rest of the segments. And this is the actual implementation and the memory cell layout. So we managed to make it still very small, very reasonable layout without making it too large. And the last problem we try to deal with is when you do this segment, you will actually leak information about your input data, about your input seed, because like if these 2 rows are activated, it means like your input number is in this range. And the attacker can look at how many like segments are activated, how many rows are activated in each segment to kind of predict what random number you are generating. And our solution to that is between each segment, we introduce this randomization scheme so that I can randomly activate some like not meaningful rows in different segments, so that that will randomize and scramble the overall power consumption. So this is the implementation, and this is the sampling results compared to the software results. You can see the hardware results is pretty ideal. In 1 million samples, we can control different distribution, we can control the parameters for distributions. And this is the energy consumption across different voltage, and also across different precisions. So this is a typical memory, like smooth plot showing that in this voltage and frequency range is working fine. So this is just working like a normal memory with a good reliability. And then we also implement a differential power analysis for the side channel attack. So you can see that if you don't turn on the masking, you can actually find the attack. You can find the correct input by looking at the power consumption. Well, if you turn on the masking, you will not be able to distinguish this correct data with the rest. And the masking apparently have a trade-off in terms of cost and efficiency, and that is shown in this curve. You randomize more, you will pay more energy, but then your attack difficulty will be increased. So this is a comparison. This is really a one-of-a-kind design. None of the previous designs, they are either based on digital architectures, implemented in digital or in FPGA, but they are all digital architectures. So this energy efficiency is great improvement. And also the area is very small compared to these digital implementations. So this one is a really interesting and exciting project. And also we consider both power and timing side channel attacks for security applications. So in conclusion, I've shown some of our recent work for PIM-based accelerator, for deep learning, for automata processing, and for random sampling. And the key takeaway message, like we think PIM principles is applicable to many computational primitives in the AI and security domains. And they provide very promising and very significant energy efficiency and memory efficiency improvements that show a lot of promise for driving the next generation hardware. So that's all my talk. Sorry for being late. Thanks everyone for your attendance.
Thank you, Kaiyuan. Thank you for a very, very informative talk. Actually, I learned a lot from that. All about the PIM, the sampling, the security part. So, any questions from the audience?
Hi, Professor.
Yeah, go ahead.
Professor. Yeah, I have a question. So in your work, MC square RM, so it is an unpublished work, right?
No, it's published. We have a ESOPAD paper.
Okay, so I have a question. In your slide, you show that when the dot product reaches about 10,000, the linearity is very good. So, I mean, in this way, there is, if you have like a 15-bit ADC, like there is no error occur in this PIM. So, but you show that on the ResNet 20, so actually the accuracy is decreased a little bit. Yes.
Yeah.
So where is the error come from?
Yeah, that's a very good question. So the thing is, we cannot fit a 15-bit ADC in the micro. So that is too large. So the ADC area is roughly like exponentially dependent on the number of bits. So we are only having an 8-bit ADC, right? And the actual number of levels we get from the computing is more than 8-bit. So we are sacrificing some information. We are losing some information during this quantization.
So the only error, the error all comes from the ADC resolution, right? There is no other error.
It's coming from the ADC resolution loss. Like ideally I want a 15-bit ADC, but now I only have 8 bits, so I lose 7 bits, right? For example. And then the ADC itself also have the error that I showed previously, like around 1 to 2 LSB. So that is extra error on top of this quantization loss.
So it comes off from the ADC.
Yes, it's mostly once you do the charge domain computing, we mostly address the accuracy problem for the computing part. So all the problem remains to be mostly in the ADC.
Okay, so have you tried that? Which is the limit during those dot product. I mean, if it reaches like 100,000, will the accuracy decrease?
Oh, you mean the memory array size?
Yes.
Okay. So for the memory array size, so there are multiple factors that's affecting what is the optimal size. So on one hand, it depends on what is the resolution of ADC. If you have higher resolution for ADC, then you can make the array larger. And typically, when you make the array larger, you get better energy efficiency and better throughput. But on the other hand, the problem is like we need to map a single filter into an array, and you cannot do two filters in the same column. So that if you make your array too large, then you don't have the real network that can occupy this entire array. And then all the extra performance, all the extra efficiencies will be wasted when you make the very large array. So those are all the constraints that you need to consider when you decide the array size.
Okay. I have a last question. So
yeah,
in your work, so what is the speed of this ADC?
What is the speed of the ADC?
Yes.
The speed of the ADC, I think previously I have the speed of ADC is roughly like 100 to 200, like between 100 and 200 megahertz. So we make the ADC quite fast. So our overall clock speed for the PIM array, it's on the faster side compared to like other state of art. Let's see, do I have a clock speed? Yeah, I don't have, I didn't list clock speed here, but our overall array speed is around like 100 megahertz.
Okay, so the overall chip speed is very much limited to the ADC speed, right?
Yes, that's correct. So that's why like you also want to have a larger array, right? So you inside this clock cycle, you do more computing. If you make your array too small, then you still pay the same delay for an ADC, but then your throughput will be much smaller.
Okay. Thank you, Professor.
Other questions from the audience? So Kaiyuan, actually, I have a follow-up question. So in your original baseline for that, the ResNet 18 or ResNet 20, so that baseline, that is based on the which bit precision?
4-bit.
4-bit?
4-bit input, 4-bit weight.
Okay. And in that case, so actually your ADC can support to the up to 9-bit ADC resolution, right?
So what I show in this curve is that these three results is assuming I have a perfect ADC.
Okay.
So even if I have a perfect ADC, then I get this accuracy. You already have accuracy loss. This I'm showing that the quantization itself is giving you this loss. It's not because of any hardware problem. And then our hardware, the actual hardware, and this is simulated. So we have a 0.3% loss compared to the ideal ADC. So that's like to show like our hardware is really like close to ideal.
Okay, I see. And by the way, so for this, the entire ResNet 20, so how do you map that on your chip, on your array? So it's
so it's just based on the filters and basically for the array size that we show here, it's mostly like we put one layer, and for some smaller layer you can put two layer, but in most cases we just one layer in one, and then you can have many micros that are in parallel working. They are like kind of pipeline or not pipeline, but yeah. So each array will be responsible for one layer.
Okay, so this the right side figure, this is for the one array, right?
This is one array, yes.
And actually you map typically 1 or 2 layers to one array, and then
Yes.
to concatenate the multiple array together.
Yes.
Okay.
Yeah. So our
during
idea.
yeah, go ahead.
Yeah. So our idea is really we want to put all the weights on chip, because we are not trying to do maybe ImageNet. We want to do these small edge applications. We don't want to have any off-chip memory access. So that's why we care a lot about the memory density. So we can store all the weights directly in this memory. And then the only thing I need to do is during inference, I do the computing. I don't need to do any weight loading.
Yeah. So in that case, so how about the overhead between the for the intercommunication between the different arrays?
Yeah, that's indeed a problem. And I think that's an architecture level problem that we are also having some collaborators that we are dealing with that part. But the good thing for this is all those communication will be in digital domain, which makes things much easier. If it's in analog, then it's almost impossible to manage. But we convert everything to digital, so you can do all kinds of like architecture tricks or designs to optimize for your interconnect.
Okay. Okay, and here because that means that you don't need any actual ADC DAC conversions between the different layers.
No, I need. So I have ADC and DAC within the array, within the micro. So then after this layer, I convert it to digital, and then it go to another array, and then the other array convert that to analog again.
Oh, okay.
Yeah, so this is kind of seemingly redundant, but based on our experience, this is really necessary for like a good signal quality. If you directly take the analog value and you try to move it to another array, the cost and the noise you get from that will be much more than your ADC cost.
Okay, I see. Okay. Thank you very much.
Yeah.
Any other questions from audience? Okay, so if no more questions, so let's thank Professor Yang again for this very excellent talk, and also thank all our audience to attend our this week's seminar. So see you next week. Thank you, Kaiyuan.
Thank you.
Have a wonderful day. Bye.
Bye.